Hey everyone, my name is Max Leamy and today I'll be presenting the magnetic braking lab. Just as an introduction, for the purpose of this lab, we observed the behavior of a bar magnet falling through a conductive tube of aluminum foil, and then we created a computational model of the magnet falling through the conductive tube. For the results of this experiment, the average time for the magnet to fall through the tube, just doing the experiment, was 1.27 seconds. The time taken for the magnet to fall through the tube in the computational model was 1.32 seconds. The magnetic dipole moment of 3.206 Newton meters per Tesla for the bar magnet is very close to the true value. For the physics concepts in the experiment, the equations for magnetic flux, relationship between change in magnetic flux and the integral of the non-Coulombic E field, magnetic force on a wire loop, Newton's third law, and Ohm's law were used. The equation for magnetic flux was used to calculate an expression for the flux through the conductive tube rings. The change in magnetic flux equation shown on the top right was used in the computational model to calculate change in flux due to the falling bar magnet. The expression on the bottom left was used to simplify the force on each wire loop in the conductive tube. Newton's third law was used to relate the magnetic force on the wire loop to the magnetic force on the magnet. Finally, Ohm's law was used to relate the derivative of the change in magnetic flux to the current through the tube. For the experiment part of this section, the system was the falling magnet and the surroundings were the aluminum foil tube and everything else. The initial conditions of the experiment were that the magnet had a velocity of 0 and it was placed at the top of the tube. The assumptions we made during the experiment were that the only forces acting on the magnet are the force from the loop and gravity. From the diagram, the black arrow represents the direction of gravity and magnetic force on the loop. Opposite the direction of the black arrow is force on the magnet by the loop, because of Newton's third law. For the procedure of the experiment, we first marked the north pole on the magnet and measured the mass of the magnet. We then measured the width of the foil, the inner radius of the tube, and the length of the tube. We then dropped the magnet through the aluminum foil tube and recorded the time for it to fall all the way through 5 times. Finally, we took the average of the recorded time to get average time to fall through the tube. For the results of the first part of the experiment, the mass of the magnet was 0.024 kilograms. The magnetic dipole moment of the magnet from Lab 3 was 3.206 Newton meters per Tesla. The length of the tube was 0.32 meters. The width of the aluminum foil was 0.006 meters. The inner radius of the tube was 0.02 meters. The outer radius was 0.026 meters, and the average time to fall through the tube was 1.27 seconds. For the first part of the computational model, I first added in my constants, aluminum tube dimensions, and the properties of the magnet shown in the previous slide. I then used the general expression for the magnetic field due to a dipole at any point to define the dipole function. Finally, I used the specific change in flux equation for the bar magnet from the physics concept slides to create the function to calculate the instantaneous change in flux over a small delta t. For part 2 of the computational model, I created my gravity vector assuming gravity pulls the object in the negative y-hat direction. I then calculated the current induced in the rings of the tube by dividing the instantaneous change in flux by the resistance of the aluminum foil. After that, I used a simplified expression for the force on the ring to calculate the force of the ring and the equal magnitude of opposing force on the magnet. I finally found the net force on the magnet and used Newton's second law to find the bar magnet's new velocity and position. This code is looped as the bar magnet falls through the tube. The results for using the computational model, the computational model predicted the magnet to fall through the tube in 1.32 seconds, 0.06 seconds longer than we observed. These two values are very close, so the measured magnetic dipole moment for the magnet from experiment 3 is very accurate. Some possible sources of error are that we had error when starting and stopping the clock while the magnet falls through the aluminum tube, error during experiment 3 when calculating mu for the magnet, not holding the tube completely straight, and not dropping the magnet from rest. For the discussion questions, I found that red corresponds to counterclockwise current and blue corresponds to clockwise. From above, as the magnet travels down the tube, the magnetic field due to the south pole decreases in the negative z-hat direction. A current therefore is induced in the clockwise direction to counteract this change in flux. This current is blue. If you flip the magnet around, the system will behave the same because the magnetic field of the magnet will flip directions and so will the direction of the current. The total time and tube for the real-world system and the computational system are very close. A computational model could be made more accurate by redefining the magnetic dipole moment for the magnet and accounting for more forces than just gravity and the force from the loop. And finally, the net force is not equal to 0 on the magnet, and the magnet deaccelerates as it moves through the tube. For the what if, what does it mean questions, if the resistivity of the conductor reduced as close to possible as 0, the braking force on the magnet would become equal to the gravitational force, and the magnet would suspend in the air without falling down the tube. If holes or slots were cut into the tube, the holes or slots would affect the ring current, and the model might predict that the magnet would fall through the aluminum tube in a smaller amount of time. If the holes and slots are very small, it would make a negligible difference. Thank you so much.